Hi, Miss Heaton here. Today we're going to talk about the ideal gas law. This is kind of a combination of the prior gas laws that you've learned. We're going to first talk about some concepts related to what this term means, and then we'll get into some calculations. So have your calculator and periodic table ready to go. First, we need to review the properties of ideal gases that we talked about back in the first screencast for this unit. First, we said that, according to the KMT, atoms have no volume, that atoms collide in non-sticky collisions, that atoms are constantly randomly moving, and that those atoms aren't attracted or repelled by each other. Oh, and finally, that their temperature in Kelvin tells us basically how fast they're moving. It's a direct proportion. So, ideal gases contain all of those properties. Now, let me give you an analogy, because there's no such thing as an ideal gas. But let's kind of hypothesize about an analogy here. Let's talk about the ideal date, right? So, an ideal date might start with a huge airplane landing in your backyard, which would be awesome. And out would walk Edward, or perhaps you're on Team Jacob. If you prefer girls, perhaps you would see Selena Gomez or Miley Cyrus. Whoever your ideal date is, maybe it's your girlfriend, boyfriend, whatever. They walk out of this plane and they take you to a nice candlelit dinner. And then you go to an awesome concert, and then the night ends with a long walk on the beach, right? This would be the ideal date. Well, I hate to burst your bubble, but you're never going to have a date this ideal. Pop. Sorry to burst your bubble. Haha. Okay, just like that, there's no such thing as an ideal gas. In fact, all gases in the real world are real, and as such, they have certain properties. The particles of that gas do take up some volume, and the particles are actually attracted to one another. Now, we can make a gas behave more ideally by altering some of the conditions, and that includes the following. First of all, if the pressure is low, so kind of like on a date, if the pressure is low, it's more likely to go well. And this is because at low pressure, that means those particles aren't going to collide very much. You know, they might be further apart, so they're not going to hit each other or the walls of their container very often. That means that those particles are relatively far apart from each other, meaning that compared to the space between them, the size of the particles is really, really tiny. So it's almost like those particles have no volume. And secondly, they're going to behave most ideally at high temperatures. Why would that be? Well, if those particles are moving really, really fast and they collide, they're moving really fast and they collide, they're going to move apart from each other really fast as well. That's really hard to show in that picture, but imagine that each of those dots are moving very, very quickly. So there's not going to be enough time for them to get attracted or repelled by one another. So they're going to behave more like the particles collide elastically. So low pressure and high temperature both make a gas behave ideally. Well, we're going to assume that the gases we're working with are ideal because it makes our calculations easier, and for most of the time that actually gets us to basically the right answer. But to do that, we're going to need to look at one more variable, and that is the amount of particles. So far in all of our gas laws, this has been a constant amount. We haven't been allowed to put more gas in or take more gas out. Now, think about this. If you change the amount of particles, the number of particles, if you add more, your mass is going to get heavier. If you take them away, your mass is going to get lighter. And we've already talked about how mass and moles are related. The more moles you have, the more mass you have. So all three of these things are related, but the one we're going to look at in our equation is moles. And this kind of leads into Avogadro's principle. This looks like another gas law, but you don't need to memorize this one. The idea that Avogadro found was that the volume and mass, or moles, are going to be directly proportional. So we can use this in combination with what we already know about the other variables to come up with our ideal gas law equation. So here's the combined gas law, right? P times V over T equals P times V over T, or equals a constant. Now combine that with Avogadro's law, which is V over N is a constant. So we'll put N on the bottom there. So now we have P times V over N over T equals a constant. We're going to call that constant R, and that's our universal gas constant. This is not the form of the equation that you want to memorize. We're going to rearrange it here in a minute, but let's kind of look at what that R means. Here's the form that you do want to memorize. P times V equals N times R times T. Sometimes we call this the Pivnert equation because if you added some vowels, that might be how you would pronounce it. So this is the form you want to memorize, and you'll want to memorize the value of R. It's a constant number, as long as you're using the correct units. We're going to use units of liters, atmospheres, moles, and Kelvin. So it's going to be very important that we always have our volume in liters, our pressure in ATMs, our N in moles, and our T in Kelvin, because the value of R is based on those numbers. You could have a different value of R, but that just gets really complicated. So we'll just convert all of our given numbers to these units. Now your teacher may prefer you to use a different version of R that's a little bit more rounded. Personally, I like 0.08206, but you can also use 0.0821 and get basically the same answer. So talk to your teacher about what you prefer, or what he or she prefers for that. So let's try this calculation. We are given 0.412 moles of helium at 16 degrees Celsius and trying to find the volume we know the volume and we're trying to find the pressure. So we can tell this is an ideal gas law calculation because we're given one of each variable, not two pressures or two volumes or two temperatures. So first you'll identify your givens. You're given 0.412 moles at a temperature of 16 degrees Celsius. If you add 273 to that, you get 289 Kelvin. We will still need to use Kelvin. Volume is 3.25 liters. Oh, we know R is 0.08206, and we're trying to find P. So you'll identify that we're using the PIV-NERT equation and plug in the numbers that you are given. Then you'll just need to do some rearrangement. It's also a good idea to put those units in here to make sure that they cancel out. So we have Kelvin and Kelvin, moles and moles, and liters and liters. So that means the pressure we solve for will be in atmospheres. So to find P, we'll just do 0.412 times 0.08206 times 289, divided that by 3.25, and you should get 3.01 ATMs. And that has 3 sig figs because all of the numbers that we plugged into our equation had 3 sig figs. And yes, we'll base our temperature on the Kelvin temperature unless otherwise instructed by your teacher. Okay, before we do another calculation, I need to talk a little bit about diatomic gases. There are some gases, some elements that are too unstable to exist alone as gases. It's kind of like Mary-Kate and Ashley Olsen or Siamese twins. These elements can't stay by themselves. If it's just hydrogen or just oxygen or just fluorine, they'll always find another atom of the same type to glob onto in order to be more stable. And we call those the Hofbrinkels. That's a mnemonic device to help you remember which 7 gases do this. So for example, if we had nitrogen gas, we would automatically know that the formula for that is N2, and it would look something like this: 2 nitrogen atoms stuck together. So you can remember Hofbrinkel, or there's other ways to rearrange that as an acronym, or you could talk about the magic 7 on the periodic table. So if you look at your periodic table and find where these Hofbrinkels are, let's look at it. H is over here on the left. Whoops, went too fast there. H, O, F, Br, I, N, and Cl. Most of them, except for hydrogen, which is weird, form a 7 on the periodic table. So you could just memorize that, or you could memorize Hofbrinkel. Okay, here's how you would see this used in a gas law calculation. A 5-liter cylinder contains oxygen at 20 degrees Celsius and 735 millimeters of mercury. How many grams of oxygen are in the cylinder? Okay, so first thing we want to do is identify our givens. We have a volume of 5 liters, a temperature converted to Kelvin of 293.0 Kelvin, a pressure converted to atmospheres by dividing by 760 of 0.967 ATMs, and we know R. So the only thing we don't know out of our PIV-NERT equation, out of P, V, N, R, T, we don't know N. So we can use PIV-NERT to find N, but the problem is actually asking us to find grams. Do you remember from the molar mass screencast how grams and moles are related? Remember that molar mass is the grams per mole. So we can use that to convert from grams to moles or moles to grams depending on the molar mass. Since we're told that this is oxygen, we automatically know that it's O2. And on the periodic table, the mass of one O is 15.99, which rounds up to 16. So the molar mass of O2 is going to be 32 grams per mole. So that's going to come in handy towards the end of this problem when we convert from moles to grams. But first we're going to do a normal PIV-NERT just like we did in our last one. So plug in the numbers that you know. You know everything except for N, and then you can just rearrange to solve for N. So divide both sides by 0.08206 times 293 and N turns out to be 0.201 moles. Then to convert that into grams, what we will do is take the moles and use our molar mass as a conversion factor. We know that 1 mole weighs 32 grams for oxygen, and we want to end up with units of grams and cancel out the moles, so we'll put 1 mole on bottom and 32 grams on top. So 0.201 times 32 turns out to be 6.4 grams of oxygen. And with sig figs, maybe we should, oh no, we only have 5.0 liters, so 2 sig figs would be the correct answer here. Excellent. Okay, here's the one for you to try. What is the molar mass of a gas if 66.2 grams in a 40.5 liter container at 25.0 degrees Celsius has a pressure of 2.5 atmospheres? We haven't done one exactly like this before, so you're going to have to think a little bit, but let me give you a hint. You're going to have to use Pivnert, and you're going to have to use the idea of molar mass. Remembering that molar mass is just the number of grams in a sample divided by the number of moles in the sample. At a bare minimum, you should be able to find N. If not, find the molar mass completely before class tomorrow. Okay, folks, so if you can do the following things, you are done for today. First, you need to be able to describe the differences between real and ideal gases. You need to write the Pivnert ideal gas law equation, know what R is with numbers and words. You need to be able to list the 7 diatomic gases, the Hofbrinkels, and solve a problem using the ideal gas law equation. To finish up here, I have a little joke for you. It has nothing to do with the ideal gas law, but you need to be careful if your piano needs repairs because you don't want to let someone who's ineptunium. Ha ha ha. I hope you have an ideal day. Till next time.